There we go. Recording is started. So it's Wednesday, October 19th. Yesterday, I was doing with you guys some of these problems. So remember, I had a short class because of the fire drill, but that's all right. We're going to be okay. Okay. Yeah, so we should be able to do the rest of those today. And I've got a demo lined up for you guys and a couple other problems. But before I dive into all that, there was a faculty meeting this morning. They were telling us about the computers that you guys are about to get. So you guys probably heard this from your first period teacher, but if not, then here's what's going on. So next Friday, October 28th, this is we're gonna have a weird schedule. You guys are gonna be in your first period class for about 2.5 hours. This is gonna be a whole process of there's like a bunch of videos you're gonna watch. There's like agreements. You guys are gonna get laptops. Check out like it's like a whole process. Then you're going to go to your fifth period class, which includes lunch, right? So that'll all be there. But then your fifth period class, you're going to do some more presentation. Then sixth period, there's some activity, and then you're going to go back to your first period. Right? And this whole day is going to be dedicated to just like processing these laptops.
Presentation or
it's really to these laptops that you guys are getting. So the school's checking. Yeah, next Friday, the school's checking out a laptop to every single student. Yeah.
What if you don't have a first period?
Oh, if you don't have a first period, do you have like a college class, or you just don't have?
No, I don't have OBS first period.
Okay, oh, here we go. Any student without first period will report to the media center for distribution process. Okay, so you go to the media center. All right, that's a great question. You got it. Yeah.
so do we do the presentation or are they doing the presentation over
Yeah, your teacher. So your first period teacher, your fifth period teacher, your sixth period teacher. Yeah, just do like presentation stuff. Right. Now, what they were telling us to do this morning is, you guys remember, I think through first period teachers, you guys got agreements. So you had to like take it home, get your parents to sign it, blah, 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 right? That has to do with like checking these laptops out of school and then bringing them back to school. So what we were told this morning is that as long as you got that agreement signed, then you can take the laptop home and bring it back to school, and it's all good. But if you did not get that agreement signed, or if your parents like specifically like don't want you to do this whole laptop thing, then what they would do is have you guys take the first few minutes of first period to check out a laptop every single day, and then take a few minutes of seventh period to check the laptop back into the media center every single day, which would like take extra time. So yeah, I think you're probably way better off actually getting that agreement signed and just like taking the laptop back, scrolling back home. All right, so here's some rope stuff. Next thing I want to do, I've got a live demo for you guys. I don't think I did this yesterday. Did I with a cup of water? No, okay. And so I got a cup of water. Oh, it's got a string. Look at that. It's got a string on it. All right, so hey, do you think there's a way I could dunk this water upside down and the water stays in the cup?
No.
How can I do that? Upside down water and the water stays in the cup. What if I swing this around in a vertical circle? Right? So let me do that for you guys off camera here. If you're watching a video at home, I'm just going to swing this around in a vertical circle. There we go. Oh, look at that. Water stays in the cup, right? Hey, do you think there's like some minimum speed to get this to work? Like, what if I slow this down? Do you think if I go too slow, at some point the water's going to fall out?
Yes.
Yeah, right. So what we're getting at is something to do with orbits. I mean, this sort of like an orbital type situation, right? So all the water's in the cup. Yeah, let's figure out what that would be, and then how it's going to connect to like satellites and gravity and the whole thing. Okay, so a cup of water going around. Okay, think imagine like you're a fish like swimming around inside. So there's all right, so you guys saw it had a string, and this was on a vertical circular path, so it was going around like this. Right? Of course, I didn't have a fish in it, but I suppose you did. And I helped anthropomorphize this situation. So, and you're at the point where the water would be most vulnerable to fall out, right? Right when it's at the top. Okay. Now let's think about a free body diagram at that point. Okay. So there would definitely be a weight, right? Could I do like mg for weight? Okay, maybe if we're at the surface of a planet, lowercase g, gravity field, we could say that. Okay. Do you guys think that there's also a normal force from the bottom of the cup pushing the water in, especially if it goes around with sufficient speed? Let me throw a velocity vector on here, v, right, which is not part of a free body diagram, but it's important for the motion. In fact, the faster that v is, I bet there's going to be a normal force from the bottom of the cup that builds up more and more. F sub n. Would that also be true? Okay. By the way, this water in the cup is nearly identical setup to if there's a roller coaster going around a vertical loop. Did we talk about that? Roller coaster going around a vertical loop? Okay, I think my other classes. Okay. So same idea. Like if there's a roller coaster going around a vertical loop, then how fast does it have to go so that you're not gonna like fall out? Okay. All right, so what I could say is that the centripetal, like these two forces would be conspiring to be the centripetal force, right? Like holding this mass of water in this fish in this this curved path. Wouldn't that be true? Okay. Like remember, for anything to stay in a curved path, there has to be some centripetal force. In this case, it's the combination of these two forces. So I can say that the centripetal force, S of C is centripetal, right? Centripetal force, okay, is the weight plus the normal force, right? So the actual weight of the water is, wants to pull the water down. So as it moves to the side, it wants to move down. Okay? But the bottom of the cup is also sort of like pushing down on the water too. Okay? Now, what if I'm interested in like the minimum speed, like not just NAV, but like the minimum speed, like the critical point, just to barely get around. Now, if it just barely gets around, do you think that fish would feel like he might be like floating around like an astronaut just for one moment if it just barely gets around? Right. So I drew a fish from the fish's point of view. Right? The fish might feel like, oh, there's no force on me at all. But from our inertial frame of reference, we're saying, well, there's a gravity force, but maybe only that force. It's kind of like if you're in a free falling elevator all the way down. Right? What I'm trying to get at is that this normal force would get smaller and smaller and smaller and would approach zero. And it would go to zero newtons. So 0 Newton force from the normal force, right? And only the gravity force would be acting as the centripetal force, right? Just if I'm solving for v in the minimum, right? So centripetal force, we have an expression for that. That comes from a lab you guys did recently. Isn't that mv squared over r? Right. So we got that. This right here is your mv squared over r, where here, let's go through these. M refers to the mass of the water in the cup. V refers to the speed, and we're solving for the minimum speed is really what we're solving for. Okay. That's the question, like how fast. And R, well, that refers to this radius of curvature here. Here's your R, that's the R. Okay. And that's equal to the weight, or the weight is providing the centripetal force. You can say plus normal force, but that went to zero. Okay. Oh yeah, go ahead. Okay. Do you guys see that the mass of the water is going to cancel out? Okay. So I could have filled like more water in the cup, but it wouldn't make a difference to the answer to this problem. Okay? Whenever you see a variable cancel in physics, think, what does that mean? Like, why would that be? Okay. And similar idea for a roller coaster going around a vertical loop, right? Whether the roller coaster is empty or filled with passengers makes no difference to what speed it has to ultimately go. Okay? Let's do something that I don't do too often with you guys, but let's solve this in terms of variables because we're just a couple of algebra steps from doing that. We can actually get the answer just in terms of variables with no numbers. Okay? Guys, can I cross multiply that r and get the minimum speed squared is equal to the gravity field times the radial size? I can do that, right? Right? And then guys, how do you undo a square? You take the square root, right? Square root. So the minimum speed for that to get around, what you guys just saw, this demo, okay, ends up being the square root of gr, where g is the gravity field of the planet and r is the radius of curvature of that motion. Okay? Now, let's solve this for what I just did, right? Because we're all locked in the same gravity field. This g is about 10 meters per second squared. We're going around into, so I'll keep that. This radius of curvature, I'm going to say that that string was about 40 centimeters long. So I'll go 40 centimeters. But I can't write the number 40 in here when I do the math, because that would imply meters, right? And I have everything in base SI units. Okay. Guys, 40 centimeters. How many meters is that? How many cents in a dollar? 100, right? Right? You guys ever bought something with cash and coins? So, so 100 centimeters in a meter. So I need to divide by 100, right? So 40 divided by 100 is that like, well, here's a fraction, 40 over 100. How about that? Meters. Okay, like that. Call it 0.4 meters. Okay. And so what is the square root of gravity field times the number of meters of radius? Okay. That is, in this case, it's 2. And the unit would be meters per second because everything is in base SI units. So you have meters, seconds, the mass canceled out already. Okay. All right, so what you guys just saw, that demo I did with the water in the cup, it had to be going 2 meters per second at least at the top. If it was going 3 or 4 or 5 meters per second, then it's okay, because remember, this is a minimum speed. Okay? But if it was only going like 1.5 meters per second, well, there'd be slack in the string and it would like start to actually like, fall down and get some water spilling and the whole deal. Okay. Right, I got that. All right. Oh, yeah, so how does this relate to like satellites in orbit? Well, instead of mg at the surface, you could do gmm over r squared, right? It's a more universal form of weight. Okay? And then you could calculate the orbital speed. Very similar algebra process to what we just did here. Okay? And then in a universal sense, the answer ends up being this, right? Which we were looking at yesterday. Right? Square root gm on r, right? Where there's a universal gravity constant, capital G. M is the mass of the planet, right? And r could be like basically the radial distance to the center of the planet, which might be approximately the radius of the planet itself if it's low Earth orbit, kind of different. All right. So yesterday we did some basic calculations. We did number 1, gravitational force between 2 masses. We did number 2, satellite orbiting a planet, which is, again, just speeds it. It's really into that demo you guys just saw. Okay. And then we did inverse square law, the force as a function of distance for changing distances. Right. Okay. And there were lots of versions of that. There were lots of versions of papers floating around. So I did lots of those with you guys. Right. So let's pick up the story with number 4. What does the acceleration do to gravity at the surface of like some planet? We switch papers here. Okay, let's do Mars. How about that? Okay. So everybody has a different type paper. You might have the planet Mars. You probably have a different planet. Right. I think some of you guys have the sun, but let's see what is the surface gravity at Mars. Well, I can use this expression right here, right? Just like force is gmm over r squared. Okay? Acceleration due to gravity is just force divided by the mass of the individual mass of the surface, okay? Which just looks like this, gm over r squared. Okay? And that's the expression we want to use to answer this question. So the gravity field for Mars would be, okay, where the G goes, capital G, I'm going to do 6.67 times 10 to the negative 11, okay, Newton meter squared per kilogram squared. Okay. For M, the capital M goes, I need the mass of the planet. Now Mars is this many kilograms, 6.42 times 10 to the 23. 6.42 times 10 to the 23. This is kilograms. And r is the radial size of the planet, which is 3.39 times 10 to the 6 meters. Okay. And don't forget that's being squared. Oh, whoops, that's meters. Okay, and that's being squared. Okay. So gravity field on Mars. Right. Now Mars is a physically smaller planet than Earth. So would I expect this number to be greater than 9.8 or less than 9.8? For a planet that's smaller than Earth. I think it should come out to like smaller than 9.8 meters per second squared, right? So if I get like 17 meters per second squared, like, okay, I probably did something wrong. Okay. All these units, crazy units, crazy units, crazy units. I know they're going to consolidate to be either meters per second squared or Newton per kilogram, okay, which is the same idea, however you want to do it. Okay, so I need a number, and I'm gonna put all these numbers in the calculator. So you guys follow along with me. I've got a quiz lined up for you. I'm probably gonna give you guys tomorrow, I'm thinking. It'll be one of these take-home quizzes, so you have a few days to do it. Okay, but you're gonna have to be able to do calculations like we're doing right here. So open parentheses, 6.67 times 10 to the power negative 11, close open. 6.42 times 10 to the 23, or whatever numbers are on your paper, right? You guys can follow along. Right? Divide by open parentheses, 3.39 times 10 to the 6, that's meters, that's the radial side of the planet. Close square, you square that radial side. Okay. All right. And again, I'm looking for a number that's less than Earth's gravity. So let's see if that's true. 3.73. I think I go with that. 3.73 meters per second squared. I mean, I think that looks realistic. So let me see if that's an answer choice. Yeah, that's an answer choice. Go with that. That is the gravity field of the surface of that planet. Okay. That's good. Number 5. Okay, a star is seen orbiting an invisible object with some given centripetal acceleration. And we figured out pretty well what is the radial size of that orbit. How massive is that object that is orbiting, right? Which would be a black hole in this case. I should probably teach that this question because there's a more conventional thing you can do, which is pretty cool, which is if you see a moon orbiting a planet, you can actually calculate the mass of the planet based on the orbit of its moon. Right? It's a question some of my other classes are doing, but this is really similar to that. We just have a black hole. Okay. And maybe it's probably too simple because I did a bunch of calculations that would help you along the way. Okay. So how this normally work is you would know what the radial size of that orbit is. You know how much time it takes to go around, and you could use that to calculate what is the centripetal acceleration. Okay, but that's already been done. So let's just cut the chase here. Okay, that centripetal acceleration would be provided by the gravitational acceleration, which is just the formula we just used to calculate the mass of the planet, the gravity field on the planet Mars. Right? Except instead of knowing the mass and solving for acceleration, which is what we did last question, now we're going to know that what acceleration is. We're solving for the mass. Right? Is that? Actually, let's solve this one in terms of variables too. Right? I mean, that's a good skill to have anyway. Right? See, usually I plug in numbers first for you guys, but the numbers are so crazy big and small. So let's just solve in terms of variables. I'll make this a little bit easier. Can you guys cross multiply r squared? I say centripetal acceleration times r squared is equal to universal gravity constant times the mass, right? And then you could divide down the capital G, right? So that mass is equal to a times r squared divided by g, right? That's the solution in terms of variables, right? Okay. And I gave you each of these numbers, so now you can just feed those numbers in. Right? In fact, you have an expression you could solve for like mass of any black hole, based on any observations, blah, 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 right? So mass of the black hole is, right, so I went ahead and told you, let's say this calculation's been done. It's like 2 meters per second squared. That's what it would have to be. Like that. And we have a radial size of like 4.7 times 10 to the 10 meters. Right. Don't forget to square that. Okay. And then the universal gravity constant is 6.67 times 10 to the negative 11 meters squared per kilogram squared. That. All right. All right. That's good. Okay, so then calculator. So you figure this out. So we got this ultimate acceleration. Got that part of the circuit, guys. We go 4.7 times 10 to the 10 meters. That's like the radius of orbit. Now that number's being squared. Then divide by, open parenthesis. It's really important you open a parenthesis after you hit divide by because there's stuff all multiplied together collectively inside. It's grouped together. So 6.67 times 10 to the negative 11. Okay. Now, if we're talking about a black hole, it's probably going to have a crazy big mass, right? And it does. Mass of this black hole is shown to be 6.62 times 10 to the 31. Now, that would have to come out to be kilograms, right? Because kilograms measure the mass. You could check that with how all the units consolidate, but that's what it would come out to be. Right? Now, for comparison, I know that our sun is like 1.99 times 10 to the 30 kilograms. Okay. So next thing I might wonder is like, well, this black hole, how massive is it compared to our sun? Okay. Now, there is some like theoretical smallest mass of a black hole to be, right? Like, how does the black hole come into creation? It comes into creation by like very large stars collapsing in on themselves at the end of their lives, right? So there are two forces that are acting on each star, right? There's an expansive force like nuclear fusion, right? And then there's the gravitational force, which is trying to collapse it in on itself. And those two forces are keeping each star in equilibrium size, right? But once that fusion runs out, the star can collapse on itself. Now, if you have a collapse that just like runs away, you have like a crazy density that results, you get a black hole. For comparison, if you took the entire Earth and you squeeze down the entire Earth to, well, about the size right here, if you took the entire Earth and you squeeze it down to this volume, that would go critical and become a black hole. But there's like no real like process to make the Earth do that. Okay? Even our sun is not big enough to become a black hole, right? Our sun's going to collapse down and become a white dwarf, right? So that's not going to quite work. But if you had a star that was at least 3 times as big as our sun, right? Then it might be just barely massive enough where it might be able to do this and collapse down to a black hole. Okay? So how about this black hole? How massive it is compared to our sun? Okay? That's actually the next question on this paper. Right? So given a black hole of some mass, how many times more massive than our sun is this particular black hole? Okay. So the way you can get that is just by taking a ratio. Okay, so a ratio equals like this right here. Okay, it's this divided by this. The ratio of the masses. Okay. Black hole compared to our sun. We can tell you like how many suns worth of mass is that this black hole. So we need to do this divided by this. Okay. Now let's do some mental math before I plug this into the calculator, because I think we can pretty well solve this just mental math. Okay. 6.6 divided 1.99, is that pretty much 2? 6.6 divided by 2, is that about 3.3? Do you guys see? Is this ratio right here about 3.3? 6.6 divided by 2 is about 3.3. Okay, so we got that. That's about 3. But then what about this part? Guys, what is 31 zeros compared to 30 zeros? Isn't this 1 followed by 31 zeros? This is 1 followed by 30 zeros. Right? What's that going to reduce to? Do you guys know that one? Who can tell me? What's that reduced to? Yeah, 10 to the power of 1, which is 10, right? Right? Isn't the rule for exponents, you could like subtract the exponents? 31 minus 30 is 1, and it's 10 to that power, so it's 10 to the 1, which is 10. Okay, so this black hole looks about 10 times the mass of our sun, but also multiplied by 3.3. So wouldn't this be 3.3 times 10, which is like 33 times? It should be about 33 times. Okay. If you figure that out without ever picking up a calculator, it's about 33 times. So it's almost like 33 times the mass of our sun, 33 suns. Okay. But let's plug it into the calculator and see that you just confirm that. I think the answer is 33. 6.62 times 10 to the power 31 divided by, open parenthesis, 1.99 times 10 to the power 30 kilograms. Okay. Let's see if 33 shows up on the screen. Oh, it's 33. 33.266, blah, blah, blah. Yeah, about 33 times. Okay. And that is the answer to the next question, number 6. We just did number 6. Okay. Let's take the ratio. Okay. How massive is black hole compared to our sun? Okay. Number 7, what is the escape speed of a rocket launched from, okay, let me switch papers here. Ooh, yeah, let's do Earth. Okay, I like that one. Okay. That's probably pretty relevant, right? So suppose NASA wants to launch a rocket and send it all the way to Mars. Okay. How fast do they have to get that rocket going so they could cut the engines and the rocket would still have like enough inertia to just like escape Earth's gravity, like fly away? How fast do they have to get going? Okay. Now, guys, do you have the expression here? I said escape speed is it's written out here. Right? I can prove that to you guys, but I'm going to save that for conservation of energy, I think. So, okay. Anyway, here's what you guys know. You guys know orbital speed is square root gm on r. We've been talking about that last couple of days. Okay. And escape speed, turns out, I won't prove this today, but maybe in the future, is a very similar looking formula. It's like the same structure, but it just has the two slips under there, right? So to connect these guys, escape speed just ends up being square root of 2 times orbital speed. Right, wouldn't that be true? Right. I'm going to solve this problem 2 different ways. Let me do one way, just the quick way, which is just to play off this expression, right? The relationship between these two. Because you guys already know what orbital speed is around the Earth, right? How fast does the satellite have to go to stay in orbit around the Earth? If you look back in your notes from, I think about the last week sometime, right? I think we got this number, 7907 meters per second, or something similar to that. Sometimes I call it 8,000 meters per second. I think 7906 was one of the calculations. It was something like that. That's how fast a satellite has to go to stay in orbit around the Earth. Well, if you multiply it by the square root of 2, it should tell you how fast you have to go. So if you were aimed straight away from the Earth, you had a rocket going like this fast. Okay. You could get away, you could break away from the gravity of the Earth and fly away forever. Okay. So look at what that would be. What's the square root of 2 times 7907? Okay. And I'm getting 11,182. I'll run that to 11,200 meters per second. You could also call that 11.2 kilometers per second. Woo! 11.2 kilometers per second. That's like 7 miles per second. 7 miles per second, right? In American units, right? So if you're going that fast. Okay, so that's one way to solve this. But let me do like the full way. So what if I actually go to this formula and I plug in all of the numbers? Universal gravity constant, mass of Earth, radius of Earth. Okay. And let's see what that would be. So the escape is the square root of 2 times 6.67 times 10 to the negative 11. I'll go ahead and take the units out here. It's giving me meters per second. We got the mass of Earth, 5.97 times 10 to the 24 kilograms, or 5.98, 5.97, so something like that. I've seen different values cited. Okay. And the radius of Earth is 6.38, I think, times 10 to the 6 meters. Okay. So this should tell me also this number. I should confirm it. Okay. Let's just make sure that works. The square root, open up a ridiculous number of parentheses. Because if I only have one parenthesis, as soon as I close it, stop square rooting. I want everything square rooted. Okay. 2 times 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 divided by open parentheses 6.38 times 10 to the 6. Okay. And it should tell me this number. I'm looking for this number to show up on my screen. Let's see if it does. Oh, yep, there it is. Right, so of course it's rounding again, but it's the same thing, 11,200 meters per second. Okay, so if you get a rocket going that fast, pointed straight away from the Earth, it's going fast enough that can break away from the gravity and fly away forever. Okay. Hey, could you break away from Earth's gravity going slower than this though, as long as the engines are on? Okay. How about this? What if there was like a rope ladder from Earth to the moon? Do you think you could very slowly climb rung by rung all the way to the moon? I think you could, which would be nowhere near this number. So you can't actually escape Earth's gravity without ever going this fast, as long as the engines are always on, as long as there's some external force, right? But if you cut the engines, then that's what this number means. Okay? Okay. Just inertia itself, you can get away. Okay, guys, good day. All right, brings us to number 8, which is another black hole type question. So a little bit of historical context here. Let's read this question first. Right? The speed of light is 3 times 10 to the 8 meters per second. This is one of the universal constants in the universe. Okay? Nobody knows why this number is what it is, but we just know that you can't move through space faster than the speed of light, which has been measured to be this number. Okay? It's actually like 2.997 something meters per second, times 10 to the 8 meters per second. Whatever. What minimal mass of a collapsed star would create a black hole if you knew the radial size of this black hole. Right? And remember, definition of a black hole is something that's so massive, so dense that not even light can escape. The gravity pull is so great that not even light can escape. Right? And I give you guys a hint here how to solve this applied escape speed equation. So the story here is that let's go back about 100 years ago. So World War I is going on, and there's this guy named Schwarzschild, and his job is to calculate projectiles for artillery. Do you guys remember back to solving projectile problems? We had like cannons set on cliffs and cannons on the ground. They were like blasting cannonballs. Where's the cannonball going to land? Okay. So he was calculating. He was making those type calculations without calculators. We're talking about World War One, right? And maybe you had a slide rule, like in the trenches back in the day. And what was intriguing at the time is there was some groundbreaking physics going on and like relativity. You're saying, hey, we have a finite speed in the world, which is the speed right here, the speed of light. Nothing can travel faster than the speed of light. You guys have probably learned that in the past. Nothing can go faster than the speed of light, okay. Like through space. Okay. If that's true, and there is such a thing as an escape speed, I wonder if there's any object out there in that big old universe that has a required escape speed that is faster than the speed of light. Because if that was true, then nothing could get away from it. And that's what a black hole would be. So he was hypothesizing this. He did some math to say, blah, 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 right? That's where we get like the term Schwarzschild radius. Remember I was saying if you shrunk down Earth to like the size of this, it would create a black hole. Right? So Earth has like a Schwarzschild radius, which would be like this right here. Right? You're looking at it. Right? So he came up with this idea of black hole. A lot of people at the time thought, okay, well, that's a crazy idea, right? But this has been observed to be true, right? There are black holes in the universe, right? And we can measure it, observe and measure, calculate like, how massive are they. Okay? So let's start with the escape speed. Okay. We're going to go square root of 2gm over r. Okay. And the premise of this question is, suppose you let the escape speed go to the speed of light, right, which is like the limiting speed of the universe. Okay? Universal gravity constant. We know what that is. Okay? Well, let's say you either estimate or have a pretty good indication of what the radial size of this black hole is going to be. Okay? Can you calculate how massive it would have to be for everything else to check out? Right? What radius did I give you guys? Yeah, let's go ahead and plug in numbers first. That's what I normally do with you guys. Okay, so let's plug in numbers. Let's let this number go to the speed of light, which is 3 times 10 to the 8, that's meters per second, equal to, it's going to be a big old square root, that 2 times 6.67 times 10 to the negative 11, 8 meters squared per kilogram squared. There's a mass that we're solving for, so we don't know what mass is, but we're solving for that. Right? And the radial size, let me get another paper, just different numbers to pull from. Right. Okay, so this paper says 45 meters. Right. You might have that paper, but you probably have a different paper. So that's like the radial size of the black hole. Like if the black hole was like an object that was like spherical shaped, Right. Has that. Oh yeah, go ahead. Look. Okay. All right. Can you guys do some algebra and solve for this m? Okay. So let's go through it step by step. Right. And maybe it would have been easier to solve in terms of variables first, but I got this on the paper, so let's go for it. Can you guys square both sides and get rid of the square root? So we can do that, right? Hey, this squared. We don't even need to calculate this. When this 3 squared is equal to 9, and 10 to the 8 squared. 10 to the 8 squared, what's that? That 10 to the 8 squared. What's 8 times 2? That's 16, right? Okay, so there's the speed of light squared. Okay. I'm gonna do something kind of weird here. I'm gonna drop the units just to make this look a little cleaner. We got 2, we got 6.67 times 10 to the negative 11. I've got a mass that we're solving for, and I still got 45 meters in the denominator. Okay, you guys, these are all base SI units. Can I multiply the 45 over? Okay, got 9 times 45. How about that? 405. Keep 10 to the 16 here. 2 by 6.67, 10 to the negative 11, then all multiplied by the mass we're solving for. Okay. Hey, I should take each of these 3 numbers and divide it down, shouldn't I? Okay. So the mass would end up being, I got this in the numerator. I don't know if I've ever saw this one this way before. But yeah. 2, got a 6.67. Okay. Ooh, guys, if I'm dividing by 10 to the negative 11, is that the same thing as multiplying by 10 to the positive 11? Right? Same thing? Right. And this is going to be some number of kilograms at the end of the day. All right. Here we go. So what is 405 times 10 to the 16, 10 to the 11? Is that like 10 to the power of 27, right? 27. And then divide by 2 by 6.67. Okay, this is going to be the number of kilograms. This is black hole. I'm looking at 3.04. Okay, so mathematically this is okay, but there's really something silly about this. Okay. So yeah, that matches an answer on the paper. Man, I really have to go back and fix this because this is smaller than the theoretical smallest black hole could be, but I don't know, but I guess it's a mathematical exercise, right? Okay. So you guys can tell that you guys can get a multiple choice answer. Okay. You guys good? Did I do that on all these? I did. It looks like. Wow, all those are smaller. Okay. Let's go hit number 10 real fast because we can do this one real fast. I think I told you guys about this. Did I tell you guys about Lagrangian points yesterday? Did we do that? Yeah. Okay. So there are some points of sort of like gravitational stability. Actually, there are like 5 points between, say, like a sun and a planet, and as long as you have orbital mechanics going on. Okay. Do you guys remember which 2 L points are considered to be the most stable? Like, suppose you were working for NASA and you want to park a satellite somewhere. Now, these could all be pretty good options, but there are 2 options that are the best. So if your satellite starts to sort of drift out of place, it'll naturally drift back into place. Okay. Do you guys remember which 2 points those are? So, sort of a trivia type question. Okay. Is it being L4 and L5? So on number 10, you guys should pick L4 and L5. Okay. All right, now let's go hit number 9. Okay. So this one is probably the most involved on this whole page. It's complex in the sense that it's going to be like a multi-step problem. So the question is, what is the orbital period of Venus? I gave you guys a hint here. Just go ahead and apply Kepler's third law of planetary motion and apply dimensional analysis. It's not the only way to solve this. You could use Newton's laws of motion and Newtonian gravity and combine that with centripetal force and solve it that way. Right? Now, Kepler figured out this proportionality between the time period it takes a planet to go around and its average distance to the star. Right? You remember these orbits are elliptical, but they're approximately circular. So we're going to say approximately circular. Okay. Approximately constant radial distance. Okay. And then if you incorporate Newtonian mechanics, then here's like an updated version of Kepler's third law. And we're going to use the updated version. Right? Well, this is one way to write it. Actually, I wrote it a different way on your paper. So one way or the other. Okay. It's the same thing, just a little bit. I'm going to switch around. All right, so I told you the distance from, let's do this paper, the sun to Venus. So what's the orbital period of Venus? I told you the distance from the sun to Venus. I told you the mass of the sun, which is the only mass you need, okay? And universal gravity constant. Okay. And if you, this is all you need. That's the only numbers you need to be able to solve this. So let's start with what I typed here for Kepler's third law. Kepler said that the ratio of the time period squared to the average distance cubed is a constant. Okay? For example, Earth takes 365 days to go around. So you wouldn't do days, you do some number of seconds, but that's conceptually what it is for Earth. Okay. But we're going to solve for what is that number for Venus. Okay. For Venus, what is this time period? Okay. And the constant ends up being 4 pi squared divided by the mass of the sun that is orbiting times the universal gravity constant. Like that. Okay. So there's a Newtonian modified version of Kepler's third law. Okay. Let's solve in terms of variables first, because there's only 2 algebra steps. Right? It's going to make this a lot easier. Right? Can I cross multiply that r cubed? You get time period squared is equal to 4 pi squared r cubed, and then mg. Like that. And then I can take square root. Okay, so the time period is the square root of all of. Oh, hey, look at this. Square root of 4 pi squared. Is that like 2 pi? And still square root r cubed mg. Like that? That what you just take the square root of 4 pi squared, took it outside here. All right. So Now we can plug some numbers in, because I told you the distance from the sun to Venus. I told you the mass of the sun, right? You know universal gravity constant. So time period is, okay, so I got a 2 pi multiplied by. I got a big old square root. Okay, and plug these numbers in. 1.09 times 10 to the 11. That's meters. That's being cubed. Okay, you guys are following along. You guys try it on your own page. Okay, the mass of the sun, 1.99 times 10 to the 30 kilograms. kg. Okay. And then universal gravity constant, 6.67 times 10 to the negative 11. Okay, and that's Newton meters squared per kilogram squared. Okay. Of course, all the units are going to consolidate, and this is going to give you some number of seconds, right? Because seconds would describe time as the base SI unit. Okay. So let's see what number I get in my calculator. Got 2 pi, got a square root, open up ridiculous number of parentheses because I'm going to square root everything. 1.09 times 10 to the 11 close to the power of 3. Divide by, open some new parentheses, group all this together down here. 1.99 times 10 to the 30 times 6.67 times 10 to the negative 11. Okay. And so I'm getting a crazy big number, which is a good story, right? Or that's a good sign. That time is, right? So what I'm getting here, getting 19 million. 19,626,000, let's call it. Okay. Because this is the number of seconds. That's the number of seconds that it takes the planet Venus to go around the sun. Right. Which of course would be an enormous number of seconds. Okay. Now that's such a big number, our brains can't really crunch it. So a better thing to do is maybe to compare this to a time unit that would make more sense. Like, how about Earth years? Right? I wonder how many Earth years that would be. Okay. Here's where we're going to break out dimensional analysis. And I helped you guys out a lot because I set you guys up, oh, look at dimensional analysis table. Look, some number of seconds, we have a number there. And then I set up all the conversions so that you can ultimately get some number of Earth years, okay, which is going to lead straight to the answer. How many Earth years does it take? Okay. So this many seconds, how many Earth years is that? Let's do that. So I got 19 million some seconds. I know that there are 60 seconds in 1 minute, 60 minutes in 1 hour. Okay, and here's where we're gonna compare to Earth time, right? So 24 hours and 1 Earth day, and then 365 days and 1 Earth year. Okay. We're comparing everything to Earth years, right? So what's 1 Venusian year compared to 1 Earth year? Right. Days, hours, minutes, seconds. The only unit on the board is Earth years. Right. You guys remember this tool? So I'm going to take my 19 million seconds, okay, and divide by, open parenthesis, all this stuff. 60, 60, 24, 365. Okay. And that's telling me, oh, I should have asked you guys before I hit enter. Would this be more than 1 Earth year or less than 1 Earth year? So if your paper has Mercury or Venus, shouldn't it be less than 1 Earth year to go around? Right. And for Venus, that's true. Okay. So I could say like 1 Venusian year, I think that's how you say that, right? 1 year on Venus is less than 1 Earth year, which of course would, because it's closer to the sun, it takes less time to go around. Okay. But if you guys have Mars, Jupiter, Saturn, I think Neptune was one of the options, okay, then it should be more than 1 Earth year, right? Okay. Okay, you guys good? All right, so I think that is perfect pause point today. Got some other stuff lined up for you guys, but we'll save that for tomorrow.